Newton's discovery of the laws of God. The scientific method of the 17th century gave rise to many world-changing discoveries. Galileo managed to mathematically describe the motion of falling objects and found evidence confirming Copernicus's heliocentric model of the solar system. Harvey documented the circulation of blood. Van Leeuwenhoek discovered single-celled organisms. Gilbert discovered that the Earth is a magnet. Torricelli studied air pressure and the vacuum. Boyle studied the property of gases. And Huygens studied waves and circular motion. But the greatest discovery was undoubtedly Newton's discovery of the universal law of gravitation, the first mathematically precise theory of gravity. Newton's discovery relied heavily on the work of Kepler, who had discovered three mysterious laws of planetary motion. Yet, despite having found these precise mathematical laws, Kepler was not able to explain them. But then, Newton showed how a single gravitational force, described mathematically, could explain both the trajectory of falling objects on Earth and all three of Kepler's laws of planetary motion. He thereby conclusively disproved Aristotle's notion that the Earth and heaven require two distinct sets of natural laws. Only one formula was needed to explain both motion on Earth and in the heavens. And as a result, it is often said that Newton unified terrestrial and celestial physics, earthly and heavenly physics, making him arguably the greatest genius who has ever lived. Never before had mankind peered so deeply into the mathematical code of the universe. And since most thinkers at the time were religious, many believed that Newton had literally found the laws by which God had created the universe. And these laws did not just allow Newton to predict future planetary positions with insane accuracy, but when in the next century a deviation was detected in the orbit of Uranus, Newton's formula for gravitation was used to discover the planet Neptune, which according to these calculations had caused that deviation in Uranus. A whole planet was discovered through a calculation. Or as one scientist phrased it, quote, with the point of a pen. So, we have a lot to get to. Let's start. Hey, good to see you. This is Stephan, author of In Search of the Sublime. On this World History channel, we'll trace humanity's relentless pursuit of scientific truth, moral excellence, and enlightenment. You'll meet anyone from Mesopotamian astronomers and Indian yogis to Greek philosophers and Enlightenment scientists. And you'll meet them firsthand using primary sources, giving you valuable insights that transcend the surface-level understanding you get on other channels. So, go check it out for yourself. Let's start. To truly understand Newton's achievement, we first have to study the work of Tycho Brahe and Johannes Kepler. In 1576, the Danish astronomer Tycho Brahe was granted an island by the King of Denmark, on which he built an observatory castle. And from this castle he conducted the most accurate observations of the motions of the planets up to that point, although still without a telescope. And with Tycho's data, his student Johannes Kepler made the next great step in our understanding of the solar system. He reconstructed the motion of the planets, as Copernicus had assumed, but in elliptical orbits, as you can see in the image below. And with this discovery, he broke with the ancient idea that the heavenly orbs were supposed to move in perfect circles. That was an idea we can trace back all the way to Plato. And this discovery of the elliptical orbits of the planets became the first of his three laws of planetary motion. The other two laws are a little bit more abstract. His second law states that an imaginary line joining a planet and the sun sweeps out an equal area of space in an equal amount of time. We can see this in the image below. If the planet Earth moves from this spot to this spot in, say, a month, then the area swept out by that line is equal to the green area depicted. And if half a year later it again takes a month for the planet to move from this spot to that spot, then the area covered is the same. The third law states that the square of the orbital period of the planets is proportional to the third power of the longest radius of the ellipse. Well, let me explain what this means. Let's look at the table below. In the first column you see the planets. In the second column I've given the orbital period of the planets in seconds. And in the third column I've given the longest radius of the ellipse, which is called A. You can see this as well in the image. And I've given this distance in meters. Now what I do is, in column 4, I take the third power of that longest radius, and in column 5 I take the square of the period. And if I then divide these two numbers, a to the third power divided by t to the second power, I get the last column. And notice that for all the planets, I get about the same result here. And this is what Kepler discovered. The square of the orbital period is proportional to the third power of the longest radius of the ellipse. Curious indeed. But although Kepler discovered these precise mathematical laws, he could not explain them. And they would remain a complete mystery until Newton published his work on gravity. The same Kepler, by the way, also conceived of a whole new way to understand gravity. While Aristotle, in ancient Greece, had claimed that objects fall because objects have the quality or the tendency to want to move to the center of the universe, Kepler instead concluded, quote, "It is the earth which attracts the stone, rather than the stone which tends towards the earth. It is not just the nature of the stone to want to move to the center of the earth, but it is the mass of the earth that causes the stone to be pulled toward it." And this is the beginning of the modern notion of force. A force is exerted on the object, and that is why it is attracted towards the earth. And revolutionarily, Kepler also concluded that all matter attracts each other. He wrote, "If two stones were placed near each other, and beyond the sphere of influence of a third body, that is, with no planets or other bodies nearby, these stones, like two magnetic needles, would slowly come together, each approaching the other by a space proportional to the comparative mass of the other." And in a letter to a patron, he even hypothesized the following: "If we were to place the Earth at rest in some space, and bring near it a larger Earth, then the first Earth would become a weight in relation to the second Earth, and the first Earth would be attracted to the second, similar as how a stone is attracted by the Earth." And this turned out to be correct. And now Newton. The British scientist Isaac Newton managed to create the first accurate theory of gravity, which he described in his Philosophia Naturalis Principia Mathematica, or in short, the Principia. To achieve this, he had to invent an overwhelming amount of new physics, and for this reason he is widely considered the greatest genius of all time, rivaled only by Aristotle and Einstein. Before he could even consider gravity, Newton first had to found the correct laws that govern motion itself, his famous 3 laws of motion. And these laws describe with mathematical exactness how objects move with or without the application of an external force. Newton's first law states that an object, in the absence of external forces, will either stay at rest or will continue its motion in a straight line with a constant velocity. And we've already seen this idea in my last lecture, where I described the work of Galileo. Without any forces working on it, including friction, if I place an object at rest, it remains at rest. And if I give it a certain velocity, it continues to move with that velocity. And this is exactly how objects move in space, as you can see in videos in the International Space Station, for example. Or in Newton's words, every body perseveres in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. His second law describes how the motion of objects changes when acted upon by an external force. He concluded here that forces cause a change in momentum, and momentum he defined as mass times velocity. So if you apply a force on an object, the value of that mass times velocity will change. In his own words, the alteration of motion or momentum is ever proportional to the motive force impressed on the object, and is made in the direction of the right line in which that force is impressed. And by the way, only for the mathematically inclined, this is today written as F is dp dt. F here is the force, P is the momentum, and T is the time. And dp dt is a way of writing the change of the momentum in time. And P, as I've said before, is mass times velocity, or m times v, which is written here. And in case the mass is constant, you can take it out of the derivative, as I've done here. And dv dt, the change of velocity in time, is the acceleration. And in this way we get to the formula that you'll find in usual high school textbooks on physics. F is m times a. This is how we now often write the second law. Well, now back to the lecture. The third law of Newton states that when an object A exerts a force on object B, then object B will simultaneously exert a force on object A of equal magnitude but in opposite direction. And we can see this, for instance, as follows. If I would push against a wall in that direction, then I would push myself away. I exert a force on the wall, and the wall then presses me back. And that is the law of action and reaction. Or in his own word, to every action there is always an opposed and equal reaction. Or the mutual action of two bodies upon each other are always equal and directed to contrary parts. So what did he do next? Then Newton used a thought experiment to show that the same gravitational force that governs the falling of objects on Earth can also explain the orbits of the planets around the Sun. And this, by the way, refuted Aristotle's theory, which stated that a different physics was needed for the Earth, for motion on Earth, like the falling of a ball, and for motions in the heavens. These to Aristotle were two different fields of study, but Newton showed that they were in fact governed by the same laws. Let's now go through this thought experiment. Newton envisioned a leaden ball being shot from a large cannon. If the cannonball is shot with a small velocity, gravity will quickly curve the ball down towards the surface of the Earth. However, if the cannonball has exactly the right velocity, then the downward curvature of the ball can be made to exactly match the curvature of the Earth. And you can see this also in this animation. If the curvature of the ball caused by gravity is equal to the curvature of the Earth, then the ball will continue to fall indefinitely without ever reaching the Earth. And this, Newton concluded, is how the Moon orbits the Earth, and also how the Earth and the other planets orbit the Sun. They're continuously falling, but because these curvatures are the same, they never reach the Earth. But they're falling just as much as an object falls when I drop it on the Earth. Newton then set out to determine a mathematical formula for the magnitude of this gravitational force. He knew that objects near the Earth's surface experience a gravitational acceleration of about 9.8 meters per second squared. So if I drop a lead ball right now, it will experience an acceleration of 9.8. And he then wanted to calculate the gravitational acceleration if you would drop the same ball, but now at the height of the Moon. And for this he calculated the acceleration needed for the Moon to stay in orbit. To figure this out, he used a formula discovered by the Dutch physicist Christian Huygens. And again, skip the formulas if you're not into mathematics. Christian Huygens had discovered that the acceleration a of any object moving in a circular orbit is equal to v squared divided by r, where v is the velocity and r is the radius of the circle. And this, Newton claimed, was the acceleration that any object would feel if you would place it at the height of the Moon. And famously, there's a story that Newton was sitting in his garden and then suddenly an apple fell from the tree. And he then thought that apple is falling near the Earth's surface with an acceleration of 9.8. What would the acceleration of the apple be if I placed it at the height of the Moon? And this can be calculated with Christian Huygens' formula. Using this formula, Newton found that the Moon accelerates towards the Earth with only 0.00273. So an apple on Earth experiences 9.8, and an apple at the height of the Moon experiences only 0.00273. And from this he could easily calculate how much the gravitational acceleration had weakened if that apple is transported to the distance of the Moon. Namely, you just divide 9.8 divided by that 0.0273, and then you get about 3600. So the gravitational acceleration at the height of the Moon is weakened by a factor of 3600. And now comes the clue. Newton also knew that the distance to the Moon was about 60 times the radius of the Earth. So if you have the Earth here and this is the radius of the Earth, 60 of those distances gets you to the Moon. But 60 squared is equal to that 3600. So he concluded that when the distance from the center of the Earth is 60 times as much, the gravitational acceleration has decreased by 60 squared. That is, the gravitational acceleration decreases with the square of the distance. If I go 60 times as far from the Earth, the gravitational acceleration weakens by 60 squared. And this is now called the inverse square law. And the inverse square law is also one of Newton's greatest achievements. And again, for the mathematically inclined, we can write this in a formula language as follows. The acceleration a of an object is equal to a constant, let's call it c, divided by r squared, the inverse square law. With r now the distance from the center of the Earth to the object. Now, using the second and third law of motion that we've discussed earlier, he then obtained a universal law of gravitation from the inverse square law, which in modern notation reads F is gmm divided by r squared. This is the famous formula for the gravitational attraction. F is the force, g is a constant, m is the large mass, in this case the Earth, m is the small mass, in this case the object falling to the Earth, and r is the distance from the center of the Earth to the center of the object. Now, how do we get to this? This was the formula from the previous slide. A is c divided by r squared. If we now multiply both sides by m, we get ma on the left side and cm divided by r squared on the right side. But ma, according to the second law, is equal to F. The second law reads F is ma. And now we're going to use the third law as well. If the Earth exerts a force on that object, then according to the third law, that object has to exert a same force on the Earth. So we can create the same formula, but now with the large m, the mass of the Earth, instead of the small m, the mass of the object. And if we then combine these two formulas, we get our final result. F is gmm divided by r squared, where g is again a constant. And now we continue. If Newton would have stopped here, he would already be among the great geniuses of all time. But for Newton, the real hard work had yet to be done. In a proof of exceptional genius, and we won't repeat it here by the way, Newton showed that only a force that follows his inverse square law can cause the planets to move in close elliptical orbits, just as Kepler had observed. Any other formula did not give close elliptical orbits. And this proof required him to invent calculus, a whole branch of mathematics. It is also called the mathematics of infinitesimal change, which allowed him to describe the changing velocities and acceleration of the planet as it orbits the Sun. Newton also developed an algebraic notation for calculus, but in the Principia, he instead used the more familiar geometric proofs to have more chance that his audience would understand him. Newton then also showed that the inverse square law also satisfied Kepler's other two laws of planetary motion. And in this way, Newton conclusively showed that the motion of falling bodies and the motions of the heavenly orbs could be described by one universal law of gravitation. And thereby he unified terrestrial and celestial physics, the physics of the earth and the physics of the heavens. But Newton also realized that although his law of gravitation could describe the motions of the planets with astonishing precision, it could not explain how the Sun could exert this force on the planets and how the Earth could exert this force on the Moon, without the Sun and the planets and the Earth and the Moon being in contact with each other. How can the Earth exert a force on the Moon without the Earth even touching the Moon? The French philosopher René Descartes had tried to solve this problem by postulating an undetectable substance in our solar system called the ether that dragged the planets along the Sun. He believed that this ether revolved around the Sun, creating a vortex, a bit similar to water going down the shower drain, and that this ether would drag the planets along in their orbits. But Newton, being a proud follower of Francis Bacon, the developer of the scientific method, he refused to include such fantasies in his theory. He said there is no evidence for an ether, so instead of making up an answer, I'll leave the question unanswered. And thinking up unmeasurable ethers is unscientific. But some of his colleagues weren't satisfied with this. When criticized about the absence of a mechanical explanation for gravity, Newton famously added the general scholium to the second edition of the Principia. He wrote, "I have not as yet been able to discover the reason for the properties of gravity from phenomena, that is, from observation. And, hear the famous phrase, I do not feign hypothesis. I do not make up things. For whatever is not deduced from the phenomena must be called an hypothesis. An hypothesis, whether metaphysical or physical, or based on occult qualities or mechanical, have no place in experimental philosophy, that is, in science. In this philosophy, particular propositions are inferred from the phenomena and afterward rendered general by induction. That is, we can only create theories based on our measurements, and after doing enough measurements we can generalize our conclusion, that is called induction." He continues, "The laws of motion and the law of gravity have been found by this method, the experimental method, and it is enough that gravity really exists and acts according to these laws that we have set forth, and is sufficient to explain all the motions of the heavenly bodies and also the sea," referring here to his explanation of the tides, which are caused by the gravitational attraction of the Moon and the Sun. Newton's achievements stunned the intellectual world, leaving the great scientists and philosophers of the 18th century in awe. Newton had created the first truly successful system of the world, which was mathematically accurate and comprehensive to a degree previously thought impossible. Never before had mankind peered so deeply in the mathematical code of the universe. And since most thinkers at the time were religious, they believed Newton had found the laws by which God had created the universe. The great scientist Lagrange supposedly called Newton the greatest genius who had ever lived, and also, quote, "the most fortunate one," For he said there could never be another Newton, as there was, quote, only one system of the world to discover. Newton had already made the greatest discovery ever made, he thought, so no genius could ever surpass him. And Edmund Halley concluded, nearer the gods no mortal may approach. That is, he had seen the mathematics by which God had created the universe. A more divine thing did not exist. During the 18th and 19th centuries, other scientists also picked up where Newton had left off, making his legacy even more impressive. Edmund Halley had searched old records of astronomical events and discovered that a certain comet, now named after him, becomes visible every 75 years. And based on this regularity, he predicted that it would return in 1757. But the scientist Clairaut disagreed, concluding that the comet would appear much closer to Jupiter this time, and that Jupiter would slow it down due to gravity. And based on Newton's theory, he then calculated that the comet would instead appear in 1758, and so it happened. His prediction had come true. Henry Cavendish solved the problem that prevented Newton from actually calculating the magnitude of the gravitational force, for he did not know that constant g that we saw in the formula. Newton had only shown that the force was proportional to the inverse of the square of the distance, but he did not know exactly how large that gravitational force was. Cavendish then solved this problem by directly measuring the gravitational force between 4 leaden balls in his laboratory. And then he used this result to calculate the mass of the entire Earth, and he therefore called this experiment, quote, the weighing of the world. The scientists Laplace and Lagrange were the first to correct a mistake in Newton's work. Newton had shown that a single planet moving around the Sun would move in an elliptical orbit, as Kepler had already measured. Yet in reality, the different planets can also attract each other, causing distortions in their motions over time. And Newton had assumed that these distortions would eventually destabilize the solar system. But since this instability was not observed, even over hundreds of years, Newton assumed that God has to intervene from time to time to restore the orbits of the planets. In his work Optics, he wrote about this: the mutual actions of comets and planets upon one another were apt to increase, till eventually the system wants a reformation. But Laplace and Lagrange then used Newton's own laws to demonstrate that the largest contributions to these distortions cancel each other out, thereby proving that the solar system will stay intact for an extremely long time. And as a result, they saw no need to postulate periodic divine intervention into the solar system. And around the end of Laplace's life, a story also began to circulate about a conversation that he had with Napoleon, although this story might be apocryphal. Napoleon asked him, "They tell me you have written this large book on the system of the universe, and you have never even mentioned its creator." But then Laplace answered, "I had no need for that hypothesis." Perhaps the greatest triumph of Newton's theory came in the 19th century, when a new planet was discovered based on only Newton's laws. Comparing the positions of the planet Uranus in various records, scientists discovered that its orbit had changed over time. And it was then theorized that these changes were caused by the gravitational attraction of a yet undiscovered planet. Le Verrier then set out to calculate the mass and position that this planet should have to explain the observed deviation in the orbit. The calculation resulted into specific coordinates, and when a telescope was aimed at this exact spot, the new planet Neptune was found. It was a sensational moment for science. In the words of a contemporary, Le Verrier had discovered a planet, quote, with the point of his pen, that is, only with a calculation. And there we have it, The Phenomenal Theory of Universal Gravitation by Isaac Newton. Thank you so much for watching. I hope you were inspired. And if you want to know more about Newton and the Enlightenment, or any other topics from world history, then read my book In Search of the Sublime. You can read it completely for free on worldhistorybook.com, or you can buy a physical copy on Amazon. Thank you so much for watching. Bye bye.